Let's turn our attention to the standard error of measurement. Now, we touched on this briefly in the previous part of this lecture when we were addressing consistency of measure. And we just talked about the intra-class correlation coefficient, which is a relative measure of consistency, and it results in a scaled coefficient because it's between 0 and 1. But if you're interested in the absolute consistency or precision of a measure, then we need to talk about the standard error of measurement. Now, this would, the standard error of measurement results in an absolute index of reliability, and the usefulness is that it's the same units as the measurement of interest. And from this, we can construct confidence intervals. Now, the standard error of measure is the standard error in estimating the observed scores from the true scores. Okay, so how do we calculate the standard error of measure? Well, there are two basic ways. Here's the first one. It is the standard deviation of your measures multiplied by the square root of 1 minus the ICC of your measures. Now the standard deviation is the square root of your sums of squares total divided by n minus 1. We've seen that before, so nothing new here. The second way is simply the square root of the mean square for error that you would get from your ANOVA table. Now generally you're going to want to report the standard error of measure in addition to the ICC. And if you want to be completely thorough, then you would also report the results from your ANOVA table. Now we can also construct a 95% confidence interval for the measured score and for the true score, if you wish, based on the standard error of measure or the standard error of estimate, which we'll talk about in just a second. Now finally, you are going to want to calculate the minimum difference that can be considered real between scores. We can now calculate the confidence intervals. In order to do so, first we must estimate the subject's true score, which is capital T, and for this we need the grand mean and the observed score. So your true score, the estimate of your true score is going to be the grand mean plus the ICC of the differences, which is between your observed score and the grand mean. Then we must determine the standard error of estimate, denoted here as SEMTS for true score. And in this case, the standard error is obtained by multiplying the standard deviation by the square root of 1 minus ICC, which you'll remember is the standard error of measure, and all of this multiplied by the square root of the ICC again. So now, in order to obtain your confidence intervals, and there are two of them in this case, the first being the 95% confidence interval around your measured score, and this would be multiplying your cut point, in this case 1.96, multiplied by the standard error of measure. But if you are interested in calculating the 95% confidence interval around the true score, then you would use, once again, the cut point of 1.96, but multiplied by the standard error of estimate. So your minimum difference can be obtained by multiplying your standard error of measurement by 1.96 by the square root of 2. Let's now consider examiner reliability statistics. There are generally two measures used. The first one, and the most obvious, is percentage agreement. So it's the percentage of judgments where the two examiners have agreed compared to the total number of judgments made. The second one is the Kappa statistic, which I'm sure most of you have heard of already. Let's look at an example for percentage agreement. So first we need the number of agreements. Now if you look at your contingency table, it's going to be the sum of the diagonals. For example, 61. The total number of cases, of course, as you know, is the bottom right margin cell, which is your total number. And in this case, let's say the total overall number is 100. So then your percentage agreement, of course, is the number of agreements over the total number of cases multiplied by 100, which gives you 61%. Okay, so this isn't too difficult. But now let's look at the Kappa statistic. So the Kappa statistic measures the agreement between the evaluations of two examiners when both are rating the same objects. Okay, so this is no big surprise here. But it describes agreement achieved beyond chance as a proportion of that agreement which is possible beyond chance. So there's the little twist to the Kappa statistic, is we're trying to see how much of this agreement is actually beyond chance alone. So how do we interpret the Kappa? The value of the Kappa statistic ranges from 0 to 1. So once again, it's a scaled coefficient with larger values indicating better reliability. So kind of a no-brainer here. A value of 1 indicates perfect agreement. A value of 0 indicates that agreement is no better than chance. So generally, what's accepted is a Kappa of greater than 0.6 is considered satisfactory or okay. The formula for calculating the Kappa statistic is simply the proportion of observed agreements minus the proportion of agreements expected by chance divided by 1 minus the proportion of agreements expected by chance. And what I've put under here is just a hand calculation using the counts from your cells from the contingency table. And there's actually a few ways you can do this calculation, and I'm going to show you an example in the next slide. All right, of course, here is your contingency table, your 4 cells, A, B, C, D. You have your margin totals. In this case, we're calling them P2, Q2 for rater 2 and P1, Q1 for rater 1. And so the calculation for your Kappa, in this case, this is kind of a simplified calculation, is 2 times AD minus BC over P1, Q2 plus P2, Q1. Here's an example with some numbers, and you can see with the calculation we get a Kappa of 0.76. So the interpretation of this Kappa we just calculated, remember it represents the percent agreement above chance, and the closer to 1, the better the agreement. And so this is just a I don't know if it's rule of thumb or what's accepted, but basically a Kappa that is greater than 0.75 is considered excellent. 0.4 to 0.75 is considered good agreement, and less than 0.4 is considered poor agreement. As we mentioned earlier in an earlier slide, we kind of said satisfactory was above 0.6. As you can see, there's different, everyone has their opinion as to what is a good Kappa, and I'll leave that up to you to decide where your threshold will be. And that brings us to the end of Lecture 2, Part 5. Next up in Part 6 will be survival analysis.